Our good friends over at Nortel, who are our benefactors today, would like to remind you to have bolt cutters.
Brian Gullickson made a good point, especially for folks on shared sites, and I know he's got at least one or two bolt cutters.
Mm-hmm.
Yeah. How many times have you had the daisy chain of locks bypassed by somebody that didn't know how it worked?
Yep, many.
Well, you teach them a lesson by putting your third lock across everybody's, including theirs.
Yeah, I've heard a few people have done that over the years. They've been real quick to make sure that the interlopers are penalized in one way or another. But then there's a lot of guys that carry files out there as well as bolt cutters. There was a picture from Albuquerque that Mike Langner shared where this guy just drives up, pulls out his bolt cutters, cuts in, starts rooting around the transmitter site up there, which is not really what you want to see. So Nortel's Tuesday thing for this coming month is going to be largely dealing with the IT issues. I'm going to have a question later if anybody has some comment about audio file conversion software, and we'll talk about that a little bit later in some tutorial programs. But right now, I'm really pleased that we've got Tom King with us today, one of the really nice guys in the industry, from a manufacturer that, well, they go more than a little bit. They take care of you. And as I said last week, the thing that just always amazes me is when I hear from somebody they've ordered a phaser from Tom, it's delivered, they hook it up, and it works right out of the box, as it were. And so it takes a lot of good planning, a lot of attention to detail, and that's what Kintronic Labs is known for. So Tom is going to talk to us, I hope, about diplexing, triplexing, things like that, and others. And we'll just turn the floor over to you, Tom.
Okay, thank you, Barry. I want to thank you for the opportunity to share with you gentlemen this afternoon, and hope it'll be beneficial. It's a subject that we have certainly been addressing for many years, going back to my father here in the company, and certainly I'll proceed right on with the presentation. So I'm going to share my screen. And we'll get on with it here. All right. Are you all able to see that now?
That's it.
Okay. So the subject is multiplexed AM antenna systems. And I'm going to talk about the following items: the fundamentals of AM multiplexing, basic network configurations for non-directional or directional multiplexing, isolation filter designs, optional tower feed approaches, AM multiplex examples, and design considerations for analog versus HD or DRM operation. Now, first of all, when we talk about multiplexing AM stations, we're referring to simultaneously applying multiple RF voltages corresponding to the multiple station frequencies and transmitter powers at the base of a common non-directional tower or multiple common directional antenna towers. The RF voltages from each multiplex station must be isolated from one another in accordance with the FCC rule section 73.44 entitled AM Transmission System Emission Limitations. Depending on the degree of frequency separation between the multiplex stations, whether it's greater than 150 kilohertz or less than 150 kilohertz, the isolation filter design will be defined. The electrical height of the towers at the highest frequency should not exceed 5/8 wave, which is the maximum efficiency broadcast tower in the AM band. Due to the narrowband nature of isolation filters, the input audio bandwidth of each multiplex station may be reduced relative to what it would be in a single frequency design. And certainly there's a lot that goes into the designs as far as trying to compensate for the effects of the filters in the overall impedance bandwidth performance of all stations considered. You need to be sure also that the tower base and guy insulators can accommodate the total peak voltage of all multiplex stations together. Now this shows a impedance chart that came from the NAB Engineering Handbook. It was produced by Ron Rackley. This shows the impedance or resistance or reactance on the left scale, and the electrical height of the tower on the horizontal scale. And you will notice that here in the region around 130 to 160 degrees is where we see impedances that are very high, on the order of up to toward 1,000 ohms resistance and reactance. And when we're looking at combining voltages, this is one thing that we have to be concerned about is the range of voltages that we're dealing with when we're producing the filter designs, because it can range anywhere from hundreds of volts to thousands of volts, and be quite significant in terms of difference between one station and another. This chart shows the current distribution and voltage distribution for a AM tower, single tower, again from the NAB Engineering Handbook. And you can see this is the electrical height of the tower from 0 to 210 degrees on the left here. And then you can see the typical current distribution here and typically for a half wave tower, as you see here, and also the voltage node being at the quarter wave point for a half wave tower, 5/8 wave tower. And this again is important with regard to determining voltage characteristics and impedance characteristics of the tower. Okay, so with regard to what drives the overall design of a multiplex system, at the end of the day, it's a matter of what are the intermodulation product levels relative to the carrier that are being produced by each transmitter that is multiplexed. And these, of course, are what would be originating in the exciter stage of the transmitter at the lowest level. We want those voltages that are coupling back from the tower from the undesired frequencies to be low enough to where when they mix with the carrier, they are not producing intermod levels that are above the allowable limits set by the FCC. And as you can see here, if the deviation from these products is in the range of 10.2 to 20 kilohertz, the required attenuation is minus 25 dB relative to carrier, and down to those products that are greater than 75 kilohertz are typically need to be 80 dB or less in terms of attenuation. All right, so this block diagram is showing what typical configuration would be for two multiplex stations feeding a single antenna. And in this case, we have the tower here, and then we have a block that's referred to as optional pre-match. And that is a network in the case, if we are looking at, for instance, a tower height that is on the order of, say, 130 to 160 degrees at one of the stations or more of the stations, then you're looking at some high impedances and sometimes some what I would refer to as high Q impedances. And so we would like to do everything we can from the overall system design standpoint to use this pre-match network, which typically may be an L or T network, to alter the original base drive impedances to where we're able to produce a flatter impedance bandwidth at the input to each of the stations involved. And then we also have your isolation filters, series trap filters here, which are the primary isolation filters to isolate the voltages that are produced, the undesired voltages at the base of the tower, from getting back into the other transmitter. And those typically we want to see at least a minus 45 dB suppression. And in the case, if you have frequencies that are, I would say, less than 150 kilohertz separation distance, then we typically may use a optional shunt filter here as well, in addition to the series filter. And that will add around a minus 20 dB additional isolation. And then from that point, we have the matching networks for each transmitter that are then adjusted to match the resulting impedance that is at the load point of the ATU back to the 50 ohm output of the transmitter with maximally flat impedance characteristics. Now, if we have more than 2 stations, then we will have additional filters here for each additional station. And we have worked with stations up to 5 frequencies on one tower. Well, this shows a typical installation of a diplexer where we have separate cabinets housing the ATU and trap filters for each of the frequencies involved. This is a diplex station, so we have 2 cabinets back to back, such that the outputs of the 2 can be then combined and fed to the tower. And you'll note the transmission lines are coming out of the transmitter relay here, feeding in the right end of the cabinet. And then we have multiple copper straps here that are fed to the ground system of the cabinets to provide adequate ground. I know this is something that Ben Dawson, I know, is encouraged, and we have learned from some time ago that in the case, particularly if you have relatively low tower impedances, it provides stability to the impedance independent of weather conditions. Now, if we turn to a multiplex directional antenna system, this block diagram shows what we have required for that type of system. And this is looking at a simple 2-tower directional in this case. And as in the case of a non-directional tower, the multiplexing takes place at the base of each tower. So depending on how many stations we will have a separate ATU and match and trap filter for each of those combined frequencies on each tower. Now, we can, of course, have situations where the host station may be, say, a 4-tower array, and the station being added is non-directional, or a 2-tower directional, for instance, in which case we have to provide detuning networks for the unused towers, which would also require isolation filters, but would require no ATUs at those towers. But for each station, we have a separate phaser cabinet, and we have feed lines going to the towers that are being fed by that particular phaser, and multiplex ATU and filters, just as we would have in the non-directional sense. And if the separation frequency between the 2 stations, or any station's multiplex, is less than 120 kilohertz, we typically recommend using these optional shunt filters at the output of the transmitter to provide some additional isolation. Now, looking at typical isolation filter designs, these are those that are most typically used for series trap filters. And they typically consist of a series LC network that is series resonant at the pass frequency. And then we have in parallel with that a capacitor or variable capacitor or inductor to parallel resonate that series resonant network at the undesired frequency, the reject frequency. So we have a series resonant at the pass frequency and parallel resonant at the reject frequency. And in the case where the pass frequency is less than the reject frequency, the parallel component is a capacitor. And when the pass frequency is greater than the reject frequency, the parallel component is an inductor. Now we can have also a different configuration, in which case we have a series network where we have a parallel LC for the reject part of the filter. And then we take the resulting reactance at the reject frequency and series resonate that with a capacitor inductor, depending on if the pass frequency is above or less than the reject frequency. And typically, the voltage, the undesired voltage that is produced at the base of the tower where the multiplexing is taking place, that voltage produces a circulating current in these filters. So in the case of the series resonant part of the filter, we have the summation of this circulating current plus the pass current of the operating frequency that determines the current voltage ratings of the components involved. Now this shows the typical topology for shunt filter networks, in which case we want to have a zero reactance path to ground for the undesired frequency and a high reactance to the pass frequency. So in this case, for the network shown on the left, upper left here, we have a series LC designed for the undesired frequency, the reject frequency, to ground. And then in parallel with that, we have an inductor to make a parallel resonant circuit for the pass frequency. And this is an inductor here for the case where F1 is less than, the pass frequency is less than the reject frequency. And then we have the similar topology with the capacitor as opposed to the coil. And then here we have, as opposed to the parallel resonant circuit here, again, we can have a parallel resonant LC with a series component to series resonate to ground for the undesired frequency. Now, with regard to the tower feed approaches that are available, we are typically looking at a base insulated tower, which is most commonly used and probably is your most cost-effective approach in most cases. That base insulated tower can be either a guide tower or it could be a self-supported tower, similar to the one shown in the background here. Or it could be a unifold fed tower, in which case you would have a 3-wire, 6-wire unipole kit on the tower and a grounded tower. Now also, in the case of certain frequencies where their frequencies are greater than 1100 kilohertz, the Kinstar low profile antenna can also be a possibility for multiplexing. And as long as all the frequencies involved are 1100 or higher, then that would be a recommendable low-cost solution. Now, from the standpoint of tower considerations, in regard to selecting the proper tower for multiplexing, if you're starting a new site, from a cost standpoint, for 2 diplex stations, if their frequencies are greater than 1100, I said the Kinstar antenna is a low-cost solution, and particularly if you have height restrictions and are near an airport, that can be a good possible solution. And I know certainly Grady Mote's antenna that would be another possibility as well. For 2 diplex stations anywhere in the band, the base insulated tower is the most cost-effective solution. A unipole tower is a very good solution for cases where the max height is 120 degrees. The use of a grounded tower opens up the opportunity for putting other services on the tower without any isolation devices required. I can tell you that we were recently involved in a project where the tower height was over 5/8 wave, and the efficiency was not sufficient. They knew this up front, so we worked with Hatfield and Dawson on this project and ended up detuning the upper part of the tower, and that worked well in that case. But it's a lot of additional expense that normally shouldn't be necessary. All right, this shows a schematic of a diplexer example. We have the tower over here on the right with the impedances shown here. This is a 1040 and 1500 kilohertz, both 10 kilowatt station diplexer, feeding a guide tower, 150 foot tower. And we have, in the case of this particular topology, we have a shunt inductor here, which is being used for some tower pre-matching. And then we have a series trap filter here. And then we also have a shunt element here. And one of the things that I'll address that with you is that something that is not, immediately apparent, but it is definitely a consideration with regard to multiplex filter design, is the fact that these components in the filter, and particularly the inductors, if they present some parasitic capacitance to ground, just by the virtue of their the proximity of that winding to ground, it presents some parasitic capacitance which can alter the impedance of the antenna. And this shunt inductor here is actually being used to anti-resonate that parasitic capacitance, so as to eliminate that as a factor in the impedance as it travels back through the system back toward the load of the transmitter. And then we have a matching network here, and we do have some slope correction here on the input for bandwidth enhancement. And then here we have the trap filter for the other frequency, 1500, and we have some capacitors here that are, this is 1000 picofarad, but they're 2 in series to make 500 picofarad in parallel, in resonant with the 25 microhenry inductor here. And then we have the ATU, and you'll notice that the meters here are on the transmitter side of the filters, and that is something that the FCC does allow, and it allows us to put them in a lower voltage environment so that they're not subject to the total voltage of the tower out here. So that's the reason why they're back here. And this again has slope correction on this ATU as well. And this shows a port-to-port network analyzer plot of the rejection of the 1500 1040 pass 1500 filter, 1500 reject filter. This graph is 7.5 dB per division, and we are looking at at 1500 kilohertz rejection level of minus 49 dB, which is in the order of what we typically want it to be. This shows a impedance bandwidth for the input at 1040 input, and you can see how we're forcing it to be as close to the resistance as we can to 50 ohms, and that's why you see this particular contour as opposed to being further out with more reactance. We're trying to, with that slope correction, we're forcing these side bands as close as we can to 50 ohms. And this shows the actual VSWR at the side bands here, and 1.6, 1.46 here at the plus or minus 10 kilohertz. Not the best, but I think in terms of this particular antenna design, it was the best that we could do. Here we show the 1500 pass 1040 reject filter at minus 57.8 dB. And there again is the impedance sweep for that particular ATU input. And here you can see the bandwidth is considerably better, 1.2, 1.09 at plus or minus 10. Here's a triplexer example. Just for example purposes, so you can see here we do have a pre-matching L network in the output prior to the feed of the tower, and we have separate filters for the two undesired frequencies with each feed to the tower. So we have a total of 6 filters, series trap filters, separate ATUs for the 3 stations. And in this case, we have shunt filters on this one particular feed based on the frequency separation. And then we have a broadbanding ATU here as well for this particular feed on this particular station. So there's a variety of things that we do depending on what the impedances are presented by the tower, and by looking at the overall topology of the network, what can be done, with filters, with ATUs, and with overall topology to yield the best results we can get at the 3 input ports. And this shows, in this case, 3 filters, a rejection of 1010 at 1230 and 1400, being around 69 dB each. And this shows a rejection of 1230 at the 1010 and 1230 triplexer ports, 60 and 40, almost 46 dB. And then this shows the rejection of 1400 at the 1010 and 1230 ports, 60 and 52 dB. So we're achieving very good rejection on all frequencies. And this shows the bandwidth of the 3 stations. And so you can see in this case that in all 3 cases that we're looking at VSWRs that are quite good at plus or minus 10, less than 1.5 to 1, which is where we typically want to be. I'm going to skip over this slide. This is in regard to the diplexing of 2 directional stations. This is WWRC and WMAL. This is in Germantown, Maryland, when WMAL moved out to 4 tower station and diplex there. when they sold their property there near the Beltway. And the reason I brought this up, on two of the towers, the impedances of the host station are quite low, 6 ohms, 8.7, 5 ohms, 3.1 ohms. And when we see these kinds of impedances and lower powers going to these towers, those are the kinds of situations that can affect the bandwidth of the overall antenna system significantly. And so one of the first things that we do when we're looking at a directional multiplex system is what can we do to improve those load impedances toward the overall improvement of the common point bandwidth for that station. As far as the diplex design approach for multiplex system for directional antenna, and with this particular case in mind, that due to the single digit resistive components, the low drive Cs, low power, we decided to design some pre-matched networks for those two towers that would allow us to boost the impedance and get it into a better regime where it wouldn't affect the common point bus impedance so much. These stations were 60 kilohertz apart, so the filtering was quite challenging, and we did have to go with both series and shunt trap filters at the towers, as well as shunt filters at the output of the transmitters, in order to achieve the necessary isolation between the two stations. So this is an example of the pre-matched network here that we added at the feed point of this tower number 3 in the host station that allowed us to improve the bandwidth. So we installed this pre-matched network before and this is the existing network here for the host station, and this is the networks that were added for WMAL. And this is tower 4, similar approach there. And then these are the shunt filters that we added at the 2 transmitter outputs here for the 570 and for the 630. And there again, these were absolutely essential to suppress the reject frequencies to the point where we're able to achieve the spurious emission limit requirement. And this shows the attenuation levels of all the filters that were involved in both systems, the series trap filters, the shunt filter at the transmitter output. And again, these are as what we determined through our overall CircuitNet model were sufficient to achieve the overall performance that we needed. Now this shows the impedance bandwidth. This was predicted for the day and night patterns for the host station. And you can see here for the plus or minus 10, we're looking at 1.6, 1.9. So we're very tight. This was based on the effects of the filters and the fact that the station was a high Q station to begin with. And on 5, this shows the nighttime 2.1 and 1.3. These were the predicted SWRs based on the design. Now this shows the input impedance bandwidth for WMAL. This was again prediction of 1.9 and 1.6. And okay, let's see here. And this is actually, this was the actual measured input impedance sweep at the end of the completion of the commissioning. And this shows the host station day and night diplex theoretical pattern bandwidth for both the, this is for 570 here. This is the plus or minus 5 kilohertz impedance pattern bandwidth. And the same here for the night pattern. So you can see that we're not overlapping each other, but we're significantly we're good on the front main lobe of the patterns in terms of what was achievable. And this shows the WMAL pattern bandwidth performance. Again, a very challenging situation. And this shows the measured intermod products that were produced and measured between the two stations. And sorry. And these that were, this one that was below level was actually a non-identified station that was not an intermod product. Did not contain the audio from either of the two stations. So all these spurious emission products were met. All right. Now I'm going to turn to digital multiplexed operation, just to address some of the constraints that one deals with when you're looking at multiplexing an HD, 2 HD stations or more. In that case, we are typically looking at the performance of the audio performance, impedance bandwidth back to the combined power amplifier stage of the transmitter. So taking into consideration the harmonic filter effects of the transmitter, as well as the antenna system itself. And we want to, at that point in the combined power amplifier output of the transmitter input to the harmonic filter stage, we want to see a symmetric left or right facing Z sweep on the Smith chart. We must take into consideration all phase shifts from the tower ATU to the input of the harmonic filter section of the transmitter. So we have to look at all the phase shift from the tower base to that point in the transmitter in terms of achieving the right orientation on the Smith chart. More stringent input bandwidth design goals are involved, typically a VSWR of less than 1.05 to 1 at plus or minus 5, 1.2 to 1 at plus or minus 10, and 1.4 to 1 at plus or minus 15 for a desired HD performance. Now this shows the MA1 waveform, which was the hybrid analog digital waveform that was the original codec used by USA Digital. Ultimately, it's now Xperi. And on the right, we have the MA3 waveform, which is the all digital AM waveform, which has strictly the primary and secondary digital carriers. So we are no longer looking at it with all digital AM. We're not looking at these primary carriers that were in the plus or minus 10 to 15 region that was causing the adjacent channel interference issues. I'll go across that one. So in the case of the antenna system, as I was saying, when we're designing for HD radio, we start with looking at the impedance sweep of the tower on the Smith chart, and then we rotate that through the phase shift of the antenna tuning unit, through the phase shift of the transmission line, and through any phase shift associated with the harmonic filter section back to the final RF network of the transmitter, combined power amplifier network of the transmitter. That's where we want to see a symmetric left facing or right facing locus of impedance locus on the Smith chart for all stations involved. So this is an example of a design where we're looking at 666 kilohertz and 828 kilohertz. This was actually an international design feeding an rhombic skirt fed tower. This is some output from our CircuitNet model showing the tower load here, the feed inductance from the tower to the ATU output. And then we have a trap filter here, and then the ATU, and then the input characteristic here. So we have the topology for both stations shown here. And this is showing the results of this particular design, in which case we have used an optimized filter design, optimized system design in our CircuitNet program to achieve a maximally flat impedance bandwidth on both stations that would be suitable for HD radio. And in this case, you can see the Smith chart sweep for both stations is tight down near the resistive scale on the 50 ohm line on the Smith chart, which is where we want it. You can see here out to plus or minus 15, we are looking at less than 1.3 to 1, 1.32 to 1 VSWR. And this is the kind of results that we really need for HD radio. All right, well, that completes my presentation, and I am very happy to accept any questions that anyone may have. Barry, I'll turn it back over to you.
Well, thank you, Tom. That's very interesting. A couple of questions have come up here, and I'll kick off with one, and that is, obviously, when you add all these filters, you're reducing the efficiency of the system. Typically, how much power or efficiency is lost in a diplex system?
I would say we're typically looking at anywhere from if you think about it in terms of if we talk about 50 kilowatt stations being multiplexed, then we're typically looking at losses on the order of 5 kilowatts. And in terms of overall loss through the combined system.
About 10%.
About 10%.
Okay. I remember seeing these huge boxes at the base of the WLS tower when I was out there, and just seeing all those filters, knowing that you were going to lose something. So now if you're doing that, obviously it's the base current that counts. So you would want a transmitter that could do 55 kilowatts, obviously.
That's right.
What about frequency differences? I know there's one diplex that never got off the ground here because the one station was 790 and the other was 1600, and that was just far too close on the harmonic. Is there a point at which you suggest maybe this won't work?
I can tell you from our experience that as long as the maximum electrical height of the tower is less than 5/8 wave at the highest frequency, and as long as the tower, we can look at, it can be, Barry, if you're obviously, if you're looking at frequencies that are on the extremes of the band, then you're typically not going to be able to have both those on the same tower, depending on unless the low frequency is shorter electrical height. say 70, 80 degrees or whatever. But I think as long as you can meet the efficiency requirements of the antenna at the frequencies involved, and you're less than 5/8 wave, then you're pretty wide open in terms of what you can do.
Maybe I wasn't really clear as could be. Yes, 790 and 1600 won't work, obviously. But if you had something, and I know you've got what, the 12, the 1020, and what is the one in LA? 1020 and 1150. So that's fairly close, but how close can you get before you say, no, you shouldn't try that?
Well, I think it's a matter of looking at the design before saying no. We have done, non-directional cases for frequencies as down to 50 kilohertz separation.
50. Okay, that's great.
For example. So as far as directional antennas, the closest we have done is that WMAL. It's now WSPZ, I think. But that's the closest we've done from a directional standpoint.
Okay. Mark Voris popped up here in the chat. He said, we got 2 AMs here in Omaha, diplexed at 660 and 1490. The tower was for 660, and for 1490 to work, they had to skirt and detune the tower.
That's what I was talking about earlier. That's the one where I was talking about, where we had to detune part of the tower in order to make it work on the upper frequency.
Okay.
And that was one where they knew initially that we were skeptical about it working, and they were very understanding about it with regard to ultimately needing to add that skirt kit.
All right.
And I hope it's working well now.
Have a question?
Yeah, it sounds really good, Tom. You guys did a real good job on that.
Great. I'm glad to hear it, Mark.
I see
Are
Tom.
there other questions?
Go ahead.
Yeah, Harold has one.
Go ahead, Harold.
So I first became familiar with these networks in like 1970, where we had a 1400 and a 1340, not on the same tower, but they were very close to each other, and they threw out spurs on 1460 and 1280. So we had to add those networks. Now, the networks that you're doing here, you're looking at, it looks like 40 to 50 dB attenuation. So a lot of attenuation is provided by the transmitter, not doing full intermod there. How much rejection do you expect to see in the transmitter, and does it vary?
That will really depend on the type of transmitter, because if it's a tube type transmitter, the output filter stages are more narrow band than in the solid state transmitters. And that's one thing that we were seeing, when we started to multiplex the solid state transmitters. We started seeing some issues develop because of the relatively wide output bandwidth of the transmitter. So, I mean, excuse me, based on using current generation solid state transmitters, the levels that we're talking about with the filters are what we have found to be suitable to yield the desired intermod products.
Okay, Ben, we have time for you here.
Well, I had a few comments on, in addition to Tom's excellent presentation. First, comment about the Omaha situation. The station got sold during the process of applying for moving the 1490 over there, and the original owners were told that this was a very bad idea, and they went ahead and did it anyway. And then the new owners weren't really real careful about due diligence, and that's why it ended up having to be modified. But as Tom and others have pointed out here, it's worked very well. And that skirting technique is one that's been used, you know, in any number of other kinds of situations, not necessarily just diplexing. Tom's comment about shunt filters being necessary for close spacing, it's not always necessary, but it's certainly very desirable sometimes to use shunt filters in situations where the spacings are pretty reasonable in order to optimize the impedance bandwidth situation. And Ron, of course, wrote a wonderful paper on that subject, which all of us use. We used to do that with a Smith chart, but doing it by simple algebra, as Ron did it, is a lot simpler and easier. Not only do inductors have capacitance to the cabinets or the mountings, they sometimes have enough distributed capacitance to have interesting bandwidth affecting or impedance transformation effects, just like static drain coils are capacitance at the upper end of the band because of those distributed capacitances between the windings. The Commission's rules call for the power output metering, or the for omnidirectional situations, for example. Directionals, the metering is normally at the common point. Non-directionals, it's normally at the tower base. But the rules allow you to use a meter at the transmitter output in either one of those cases. And also they allow you to use the transmitter output power meter if it's one that takes into effect the phase between the current and voltage. And most modern transmitters do, in fact, qualify. And I've been told that all non-tel transmitters ever manufactured, in fact, meet that requirement. But you can put the meter location just darn near anywhere in the system if you explain to the Commission why you've done it. And we've put them at the input of the filters, at the output of the filters, and elsewhere sometimes in the system in order to, at the ATU input, sometimes in order to be able to get a metering situation that isn't affected by the second or third frequencies. Tom's point about modern transmitters being sometimes more critical to deal with in multiplex situations, it's particularly true, we found, when they first started making solid state transmitters and they started being installed in existing old diplex systems. The losses in the systems frequently are not as high as Tom has provided. I think that's a pretty worst case situation. In a lot of cases, we find that there are less than that. Typically, of course, any complex directional antenna system has got I2R losses in the coupling and other components as well. So the losses aren't all that different from a complicated directional antenna system. And once again, Tom's presentation was really an excellent outline of all the things you have to take into account. But the most important thing is to deal with it as a whole system problem, and not just look at the individual parts and pieces. And when you do that, you find that sometimes odd things can make changes that are very desirable, and things that don't look very odd can sometimes really bite you. The other thing is pre-match networks sometimes can be designed so that the input impedance at both frequencies is a purely resistive load. And that's ideal for the performance of the bandwidth of the filters, that bandwidth performance of the filters that precede it in the system. And with that, I'll shut up and let somebody else talk.
Thank you, Benjamin.
There was a question somebody put in the chat about how do you drive antenna monitors in these multiplex DAs?
The antenna monitors, just as the towers, the feeds to the antenna monitor require trap filters. And Potomac Instruments provide trap filters for those. And they design them for the specific voltages that are being coupled back from each tower sample system.
On a quick note, Tom, on your picture of 43 of the rhombic antenna skirt feed tower, if you can pull that up again, I had a question on that.
All right. You see
No, it was
that?
off. It was 43. It was the rhombic.
Oh, well, now,
I think he's talking about your Kinstar.
you talking about the Kinstar.
No, it wasn't the Kinstar. It was after that. It had to do with the 666 and the other frequency.
Oh, okay, okay. Yeah, okay.
That one. No, you just passed it.
Yeah, that.
It's the one before. It's the one before that. Yeah. So here on the bottom one for the 828, I see it as 103, but yet the phase goal on the opposite side was minus 103, 180 degrees out. Am I reading that right, or am I just missing something there?
Well, the total phase is 103 degrees.
Okay.
That's what it's saying there. That's what that's showing.
Right, but next to that it says phase goal and it's minus 103. So isn't that 180 degrees difference?
Okay, I see what you're saying. Yes, that's 180 degrees out from what's the total phase that's shown. That's right.
Right, and the same on the top is minus 75, and then it's showing 75.
Yeah. So that's to give us the desired orientation at the common point of the combined amplifier output of the transmitter.
Oh, at the transmitter. Okay, all right.
Yeah.
All right.
And this, and you bring up the fact, as I said before, this was an international case, and this was feeding a rhombic skirt. It's a diamond-shaped skirt, which is not authorized in the U.S., but is we have found to be a very good antenna for multiplexing multiple stations and yielding good bandwidth characteristics, as you can see from the results here. But it's not authorized in the U.S. because of the horizontal polarization component that is incorporated from that design that the FCC doesn't like.
You mentioned during the presentation that you had done one with 5 frequencies on one tower.
And that was a rhombic skirt fed tower in Mexico.
Okay. Did you find that more difficult than or did you find that fell in?
Well, it definitely had its challenges from the standpoint of bandwidth, isolation, not so much, but trying to achieve the best possible bandwidth on all 5 stations was quite a challenge.
Some compromises, obviously. Yeah.
That's right.
There's
a site, Barry, in New Zealand. I imagine Ben is aware of this. That they had 2 towers on the same site, and on each of those towers they had 6 frequencies multiplexed. So they had 12 multiplex stations at that site. They were all 10 kilowatts or less, but that was something that's the most combined stations I know of anywhere in the world.
must have been a huge set of filters. Did you your software that you put this stuff together with, did you do this custom, you or Bobby? Or
I will tell you that Jim Moser, our engineer who's been with us for 25 years, he's been responsible for the software development, working with college students in the summers. This is something we started many years ago, really after Jerry Westberg's, you all recall Jerry Westberg's software, which is quite good. We basically took that whole concept and developed it further and have been improving it since that time. And as Ben was indicating, you see these green dots on here, that's where we combine the 2 feeds together in the model. And you have to look at it from the standpoint of a overall port-to-port system. Otherwise, you can get out, you can build something, get out in the field and find that that the results are much different than what you thought. And so the CircuitNet program that we use, it allows us to look at any type of topology that we want to look at, and allows us to look at overall system performance and start, manipulating various components and various topologies to get, what we think is an optimal design. And then we have another program called ArrayPat, which is used to optimize pattern bandwidth. So we're looking at impedance bandwidth and pattern bandwidth together.
And judging from the slides that we saw, the actual outcome seems to be very close or better than the predicted, which is good to see.
Well, it's based on a lot of empirical results, building systems and trying to refine the modeling effort, which has resulted in much better predictions today, and certainly true of HD systems.
Tim Sawyer asks if you or Ben could talk a bit about antenna monitor sampling with multi-DAs.
I already passed that question on, and he answered it.
Well, as I said, the Potomac Instruments design and supply filters for multiplexed feeds from a multiplexed antenna system. So any time that we're looking at a multiplex system, we have to have a separate antenna monitor for each antenna system. And they will require isolation filters that Potomac will design and fabricate and incorporate into the antenna monitor. And we're talking typically, I think, somewhere 10,000, probably to $20,000, depending on the complexity of the multiplex system.
Well, that's the point, isn't it? That this is not something that you do on a dime. It's something that you plan and you execute to accomplish the goal.
So how does the Gorman-Redlich units do it without the filters?
Say again?
The Gorman-Redlich, I can't pronounce, maybe I'm saying it wrong.
Oh, yeah.
But they have the antenna monitor that doesn't need the filters, because I have a Diplex, and that they put 2 of those in. I don't care for them. I ended up switching mine to a Potomac after fighting with management on the cost, but I got it done.
Well, that's I know Jim Gorman had talked about providing antenna monitors for that kind of situation, and I'm glad to hear that you have some experience with those. And if you are satisfied with the results, then that's certainly good to know.
Well, they worked out fine in the beginning. It's on WZRC, and I can't think of the sister station. 1310 is, I can't even think of the calls. It's Radio Christiana. But we ended up putting 2 of them in. They worked fine till I happened to have a lightning strike on it, and I wasn't getting proper readings, and I had a hard time because I had to manually rotate through, excuse me, to see each of the antennas. It's a 4-tower array, so to switch through each of the 4 towers was a pain in the tush connecting it to the Burke. So that's why I like I said, I fought with management, and I finally got a Potomac, because I get all 4 towers phase and ratio right into the antenna, into the Burke, and I can see everything remotely just at a glance. But it's a good unit. I mean, they're still using it on their end. I just switched mine to Potomac.
As I recall, a Potomac is a wideband instrument, and a Gorman-Redlich, I think, heterodynes down to a low frequency, and perhaps the other channel is outside the bandwidth of that.
Yeah, I don't know.
I think that's right, Harold.
Okay, I've got Richard. Did you want to speak here? I just have a little eye from you in the chat. Perhaps not. You mentioned the low profile antennas, Tom. And just like to stop and jump on that for just a second. And you said that above 1100, if I remember correctly.
The reason I said that, Barry, is that that's about the limit of wooden utility poles that are available that will yield a low cost solution for the Kinstar. If we go to higher than 1100, you have to go to steel towers to support it, and that becomes cost prohibitive.
Okay. Yeah, you and Grady both working on very similar goals here to reduce the footprint or the height of these antennas, especially where you have zoning issues and things like that.
Correct.
Richard, I hear you typing furiously.
Yes. Let's see. Am I in? Let me unmute myself. Yeah. Okay. I've been very impressed in a number of cases with stations I've been connected with that Kintronic seems to have documentation going back almost to the beginning of time. And I'm wondering, Tom, how far back does your documentation go?
As far as the time that my dad was here, that could be back in 50s.
So he started that off as part of the institutional commitment of Kintronics to do that, I guess.
Well, you know, we, you know what, the documentation back at that time was definitely all handwritten or, you know, blueprints and that kind of thing. And we have made an effort to go through all of our old files and scan them. We have a large scanner plotter that we use for drawings, and so we have tried to take out older files. I know our son Josh, you may be referring to one that was just recently sent that dated back, I think, to the 70s maybe or 60s, I don't remember, but it was a blueprint that we had in a folder that was for that particular station and that we had in a file, and we had not scanned that one. So, but we were fortunate to find it in the file that we have. You know, we have file cabinets going back that far, and we make every effort to keep all of our documentation organized and on computer where we can get to it fast. And so, yeah, we are trying to, be proactive with regard to the industry, and realize there are still a lot of older systems out there, and which oftentimes, we're talking to people, they want to know, well, what kind of contactor is in my system, that goes back to the, 50s or 60s, 70s. And we typically, hopefully can find out the information they're looking for without them having to send us pictures or whatever.
And every year they get older.
Well, we're thankful for the digital age, Richard, and it definitely makes things a lot easier. And we, with database searches and everything, we can access so much information now that we couldn't a long time ago. And so, yeah, I'm glad we were able to help in your situation.
Well, I can't think of any other company off the top of my head with 3 generations that have been such an instrumental force in the industry. And so I just have to offer my congratulations and the fact that I'm impressed. Well,
we have been very blessed, Barry, and very, very fortunate and thankful to God. I'll just tell you up front, we are blessed as a company, and we have staff here. I'll just tell you, gentlemen, that have stayed with us through the thick and thin of the economic downturn. We had to go back to working 4 days a week, for quite a while, and nobody left. 20% pay cut, and that's the kind of people we have here. They're a team. They love what they do, and they're doing some exciting things. And I encourage y'all to come visit us sometime if you're this way. We'd love to show you around. We've just incorporated some new equipment, machinery, and so we'd welcome y'all to come visit us.
Love to be able to do that one of these days before too long. We still have, I think, on the BDR here, the video that we did with you folks on working on contactors, if I remember correctly. And
yeah, we're working on some more of those, Barry, that we hope to share with you soon.
good. Look forward to that.
Good point, Barry. Hey, Tom, I recently replaced one of your contactors at one of my stations, and the holes did not line up. Thankfully, that contactor sits on the floor of the phaser, and when it bolted everything in, it locked in place, but it's not bolted to the chassis. Because the new solenoids are larger?
Yeah, because we have a retrofit kit, where you have, in order to change solenoids, you have to modify the front end of the contactor. Because that was an issue with the solenoid providers, and we end up having to go to that retrofit kit in order to accommodate that change.
I mean, it was a whole new contactor, but the holes on the new contactor did not line up with the holes in the phaser at all.
Yeah.
Not changing solenoids, just replacing the whole contactor.
Okay. Well, in that case, we had to extend the base plate of the contactor a bit, and that moved one of the, I think one of the mounting holes.
I think it was 3 on mine. I think I got one screw in, that was it.
Okay. Well, I will, that's a good point. Because I'll certainly attend to that situation with our staff. Lark Hadley, how are you doing?
I'm good. I just wanted to say hi and say, it's spectacular how many people know you internationally. When we did that project in Israel, I thought that you were everybody's uncle.
That's because I love Israel. I love the people of Israel, and we would do anything for those folks.
Yeah. So anyway, I was just going to say, I guess you've made so many contacts around the world internationally that you how do you keep track of all of that?
By email. I'm in contact with people day and night. I get calls at midnight or 1 o'clock in the morning, blah, 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 blah. But, Ben, if he's still on the call here, we did the project over there in Shiar Yeshu with a triplexer for the IDF and Voice of Hope. And Ron and Ben and Stephen Lockwood was involved in the commissioning on that. And we supplied the equipment, and it was a situation where we planned about 10 days to install this whole system, get it up and running. I was over there and Stephen was there. And because of Israeli customs and issues with Israeli customs, by the time we got the equipment to the site, we had 3 days. And I mean, we finished it on the air in 3 days. And it was a great team effort on the part of the IDF guys and Stephen and whole crew from Bezic that were there. And, it came off. And, but yeah, we have a lot of friends around the world. And
Well,
it was-
exciting thing.
It was one of those that dropped in and turned on. I remember Stephen said, well, that was easy. And that was a 3 station. So that was, there was a lot going on there. So thank you for helping with that.
If I can make a comment, and that is that every time I've had dealings with Kintronics, I call on the phone or talk to whoever, and it's like I'm dealing with friends. This is not the case with many companies these days, but when I'm dealing with Kintronics, I'm talking to them. It's like I'm dealing with good friends. Thank you, Tom.
Bert, we, as I say, I think a business that's a business is built on relationships. A successful business is built on relationships, as Barry will attest to. I mean, it's those friendships that start with a meeting or a call, and that continue for many years. And I cannot. I'm very thankful for the friends. I'm thankful for all of you. We want to continue to be a company that is striving to get better and better. We don't want to sit still, and we want to. We're going beyond broadcast and significantly in some areas, but we're going to be here. We're going to be here to support the broadcast industry for a long time to come. And we've got great engineers, we've got great equipment, and we've got a team here that believe in craftsmanship, and we don't cut corners. And if we have problems, we want to hear from you, just like Neil, that issue with the contactor replacement. Those are the kinds of things, we're ISO certified, and we got to make it better. And any kind of negative feedback, don't hide it, talk about it. Tell us about it. Call us.
Not the only negative thing I can say is that in my experience at the NAB, it's hard to get into your booth. You have such an array of people that come to visit and share their knowledge. It's like going to a university and seeing all the dons together. They're at your booth, and I think it's just amazing expression of the way folks feel about you. And really, that's the key.
Well, our focus has got to be on service to our customers and quality products and timely delivery.
I'll also mention that what was it, 13 years ago, something like 14 years ago, when at Radio Guide we did those AM transmission seminars, and I called you, and you and Bobby came right on out and shared a lot of important things with us.
Very good.
Really appreciated that.
Well, we were glad to help, Barry, and we want to be a team player and help anyone in the industry that we can help, and work with all the other companies involved. I know Kurt Gorman and Phase Tech and certainly any others that are, we want to help where we can help and be a good player, be a supporter of the industry and help everyone survive in these challenging times.
Sure. Well, look, here's Tony Owen. He says he stopped by the factory at quitting time and you rounded up the parts yourself.
That's very possible. I drive a forklift and do everything from that to climbing towers. So one thing that I want to just bring to the attention of each of you while I have you here, and that is regarding the National Radio Standards Committee, the AM Improvement Working Group under that committee, and under that Improvement Working Group, we have an RF noise task group. And we are in the process of preparing a white paper that we hope to present to the NRSC at the NAB Spring Show. And in that, we're wanting to identify 5 major contributors to the RF noise floor. We are working with ARRL, with Ed Hare, who is heading up their lab, and they have a significant database of noise source identifications by members of ARRL that they've maintained over the last 15 years. But I want to encourage each of you and your client stations to, if you know, or if you have documented evidence of RF interference to any stations due to specific causes, whether it be overhead power lines, whether it be LED traffic lights, whether it be, switching power supplies, I would encourage you to let me know, because I'm chairing this committee, and we want to comprise as much data as we can, because we are working proactively with the regulation group at the FCC. And anytime that just for instance, Ed Hare brought to our attention a particular light that they just discovered the conducting noise associated with that light exceeds the FCC limits by 30 dB. And that's something that's being reported to the FCC. But anytime any of you have any evidence, it could be a video clip on your phone, recording of, you're listening to a station and you're getting particular interference that is coming from something. Send that to me. And thank you, Barry, for putting this together. And I appreciate everybody's attention today.
Our pleasure. We want you to come back. Talk to us. Talk to us about FM filters or isocouplers or maintaining something.
Okay. Maybe we'll get Josh on here the next time.
That would be great.
How many people know that your company also provides pressurization equipment for transmission lines?
Yes. Yep.
We bought one, and it's just very well made, and performance-wise and price-wise, you do much better than some of the other more traditional brands you've had out that other people sell.
Yes, sir. It has the dual drying chamber, and it's that's one of the things that's good about it. It has redundancy built into it.
Yes.
And I'd like to talk to you about the dummy loads.
And the FM dummy loads is something that people don't associate us with, but we have been offering FM dummy loads from like 5 kilowatt to 75 kilowatt. Well, I guess for the last 4 or 5 years now. And the FM combiners, we supply coaxial switches. We can provide everything except the antenna at this point.
Well, we've got a lot of opportunities to do some of these. Looking forward to it.
We supply equipment, for lower frequencies, higher frequencies as well. And we do a lot of custom work. We do a lot of government, military work, some pretty unique stuff. Come see us. Thank you all for your attention.
Thanks.
So look forward to seeing you all again on another various meetings here.
We'll make sure.
And all the best, everybody. I hope you stay healthy.
And your family as well.
Thank you, Mary. Bye for now.
Bye now.
Sierra, number 4, letter U, AVS for you.
Okay.